everyone, my name is Meiling Fang. Today I will present our work titled Face Presentation Attack Detection by Excavating Causal Clues and Adapting Embedding Statistics. Face presentation attack refers to using a presentation tool for the face recognition systems, such as printed face images, recorded videos. Presentation attack detection, which automatically detects such attacks, is important to secure face recognition from presentation attacks. Recently, face PAD algorithms have made great progress on the intra-dataset scenarios. However, face PAD algorithms have some limitations. First, when facing the more realistic cross-domain scenarios, face PAD performance significantly degrades. Then, some researchers proposed the domain adaptation-based method, which uses a small subset of the target data during the training. However, such data is typically unavailable in real-world scenarios, as we don't know which kind of attack will be used by attackers. Also, some domain generalization-based methods are proposed, which need to have domain label of each source dataset. They attempted to elevate the problem caused by the different data distribution and do not study the intrinsic causal mechanism. Moreover, most of the existing domain adaptation or domain generalization-based face PAD models are computationally intensive, such as using VIT as backbone. To address such issues, in this work, we propose a causal inference-based method. Causal inference is used to analyze the correlation between the variables and the final result. We first model the combined DG-based PAD task from a causality-based view, as shown in this structural causal model. There are three variables. X is the face input, Y is the prediction, and Z is the high-level feature representing the PAD task XZ to Y. In practical, we can analyze the causalities by manipulating the values of the variables and observing the cause effect. And this manipulation is termed intervention in causal inference and represented by symbol do. Now, let's link the intervention with the model optimization. First, we recall the convention empirical risk minimization. X is the input image and the Y is the label. PXY represents the training data distribution. H is the model and A is the loss function. Model can be trained to minimize this risk. If we consider an intervention, the risk will formulate like this. So the training data on this intervention, and the worst case will be written like this equation. And finally, we can have a generalized model by solving this min-max optimization. However, it is very challenging, but it can be approximate from two aspects, which is related to this term. Here is overall pipeline of the proposed solution. Two main contribution parts are CG MixStyle and the counterfactual intervention. Let's recall the equation. First, we can approximate this equation by enriching the diversity of training data distribution. However, due to the privacy concerns and the label-intensive nature of the data collection, most existing face PAD datasets are limited in identity capture environments and attack types. Therefore, increasing the training data diversity by using more training data is the less realistic option. A recent introduced work attracted our attention, named MixStyle. This method increased the distribution of the available limited training data by mixing the feature statistics. This method has two shuffle operations. One is random, the other one is the shuffle guided by the domain label. However, face PAD relies on the subtle intrinsic attack clues that are assumed to be part of the image style. Therefore, both shuffle operations pose a potential risk of the degradation in PAD performance, as the style transfer may be performed between the bona fide and attack samples. Therefore, we propose to modify this mixed style concept by restricting the shuffle operation within the same class. This class-guided mixed style can produce more diverse features without a confusion of bona fide and attack features, and then resulting in a better generalized representations. Let's go back to the optimization again. We can also approximate the equation by increasing the diversity of intervention. We build an assumption regarding the high-level feature Z that each feature representing for image X is constructed from a mix of the different factors, including causal and non-causal factors and spurious factors. We propose to perform intervention on the learned feature Z. In this work, we propose to perform counterfactual intervention, aiming to generate a counterfactual sample where the causal factors are removed. However, generating these true counterfactual features is impractical because the causal factors in high-level feature is unobservable and unformulated. So, we use 3 simple interventions: random zero, random shuffle, and random replace to encourage the model to uncover the causal factors from the confounding feature Z. This uncovering is facilitated by comparing the effect of the original feature Z and the counterfactual features. So this is a Hopper pipeline, and the loss function is a combination of the original difference and the causal effect. In experiments, we use ResNet 18 as our backbone, which is also widely used in FastPAD research. We use 5 public available FastPAD datasets to perform cross-dataset evaluation. And note here, the set-based spoof dataset is the large-scale dataset. We first compile our CG MixStyle with the existing MixStyle method. In OMI, to see case using random MixStyle achieve the worst result, which confirmed our worry that mixing the feature between bona fide and attack will confuse the model, and our class-guided shuffle operation enrich the feature without confusion, and we can see that CG MixStyle obtains the best average performance and the lowest error rate in most cases. Then we investigate the effect of the different types of the counterfactual interventions. Here, all refers to randomly use one intervention in each training mini-batch. This combination performs as a single CIs, proving that increasing the diversity of the intervention helps model optimization. Now we start to compare our method with the state-of-art PAD algorithms. The first scenario is multi-source cross-dataset evaluation. 3 datasets are used in the training process. Methods in the first block are conventional PAD solutions, which means no domain adaptation, where methods in the second block are designed to target the domain shift problem, which means domain label or a small subset of the test data is used during training. The board number indicates the best performance on each protocol. Our method demonstrates a very competitive PAD performance. When we test on a large-scale A spoof dataset, our solution achieves the best performance compared to the state-of-art result. Then we conduct limited source cross-dataset evaluation, where only 2 datasets used during training. Our approach outperforms the other PAD method, further proving the generalizability of CG MixStyle and CI modules. We also evaluate the CFPAD under the highly challenging scenario where only 1 dataset is available for training. Our method improves the PAD generalizability in most cases and achieves the lowest average error rate. In addition, CFPAD improves the worst case. This plot is the performance variation under single-source cross-dataset scenario. Our method performs more consistently than other PAD solutions in the challenger scenarios. In addition to performance improvement, our method is efficient because both components have no extra trainable parameters during the training and will be removed during the inference process. We count the trainable parameters of models and the floating point operations of our method and the existing PAD works. When we look at the plot, the ideal solution will tend to be placed on the bottom left corner, which means low error rate and low complexity, as well as small circle, which means less trainable parameters. The proposed method achieves the lowest flops and very competitive PAD performance, indicating its relative high efficiency. So here is some take-home message and our paper and our code. Thank you, everyone.